Okay, so this is the third lecture on 10.4, and we just finished talking about the integral test, which basically says that right, if we form an integral, improper integral, based on the series that we're given, and that integral converges, that means that the series converges. If the integral diverges, that means that the series also diverges. Alright, more examples. So example 9. And we have something like this, and 1 infinity 1 over n cubed. Okay, as usual, couple terms. So the first one 1, then if n is 2, 1 over 8, 1 over 27. Okay, so we can see that the terms are tending to 0 quite quickly. So my suspicion is that I would think that this series converges, okay, but we don't know for sure, so we need to check it. So my corresponding function would be 1 over x cubed, and we know, right, we need to form that, right, that integral from 1 to infinity, and then its limit with b approaching infinity, and the integral from 1 to b, 1 over x cubed dx. So it's a pretty simple integral. So we're getting limit at b to infinity, and here I have minus 1 over 2x squared, and the limits of integration are b on top and 1 on the bottom. Okay, so let's plug them in. So I will have 1 over, or negative 1 over 2b squared minus 1 over 2 times 1 squared. Okay, it's a negative, so this will be plus. Okay, so now if b tends to infinity, well, this whole thing, this tends to some big number, so this whole thing will tend to 0. So this approaches 0, and this is just half, so the limit is half. So now our conclusion is integral converges. So therefore this series converges. Okay, but don't assume it converges to half, right? We know that that's not true. Yeah, I'm not sure if we know what it converges to or not. I don't think mathematicians know. They can approximate it, but I don't think they know exactly what it is. Anyway, another one. So n equals 1 to infinity. Okay, so 1 over square root of n. So my corresponding function will be 1 over square root of x. And, right, we know what to do. So from 1 to infinity, I guess we could write couple terms, and we will see that those terms tend to 0, right, as n approaches infinity. So we cannot tell for sure what's happening. Let's do our integral test. So here is my integral 1 to infinity. I have x to negative half dx. So then, right, I find the antiderivative, and that's just going to be 2 squared of x. Okay, and the limits of integration are 1 and b. I plug them in, so I have limit with b approaching infinity. What do I have? 2 square root of b minus 2 square root of 1. Okay, so this is just 2. But this, yeah, so if b approaches infinity, then this whole thing also approaches infinity. So that equals to infinity. Now the limit doesn't exist, so the integral diverges. So our conclusion is series diverges too. Okay. Is there some pattern? Maybe. Maybe there's a pattern. Anyway, the next one, I want to show you one more. No. I think we have maybe enough examples. I'll give you a couple problems in a moment. I just want to point something out before we get to problems. So, 3 series that we just did. 3. Right, we had those. We did one was the first one was 1 over n cubed. So 1 to infinity. So 1 over n cubed. So this one converged. Okay. Then we had this one we just did. So that was 1 over n square root of n, or n to 1 over 2, right? So that diverged. And we also had this one with just the harmonic series, right? So n equals 1 to infinity. And we had, let's write it 1 over n to the 1. Okay? 1 over n, or 1 over n to the first power. And this also diverged. Okay, so there's a pattern, right? So all this type of series are called p-series. Let's write theorem about p-series. So p-series look like this. Let me maybe write it here. Maybe here. This is a general formula for p-series. So n from 1 to infinity, and then 1 over n to p. Right, so your terms would be 1 over 1 to some power p plus 1 over 2 to p plus 1 over 3 with exponent p, and it keeps going. Okay, so that's p-series, and we can see that all 3 of those are examples of p-series. So now the theorem, right? We can see that. Right, so here I have p is 3, p is half, and p is 1. So we can see that so p-series converge if p is greater than 1, and diverge if p is less or equal than 1. Right? And our examples confirm it. Right, so that's the theorem. Okay, What else? Yeah, let's think about those three conditions, right? So of course, not every function is positive, decreasing, and continuous, right? So let's maybe look at an example of a function that is not positive, maybe. So keep in mind, that's a bit of a warning. It's a good idea to check, right, those three conditions. So the function must satisfy three conditions, but sometimes it does not. So what are the conditions? Positive, right, well, it's all for n greater or equal than 1, and then continuous, and decreasing. Right, so the function needs to be decreasing. Okay, so here's an example. N equal to 1 to infinity. So I have minus 1, and here I have n plus 1. And other than that, this is just a harmonic series. Okay, so what is happening here? Let's write out a couple terms. So the first one will be 1, right? So for n equal to 1, I'll have square. Yeah, I have a square here, right? So that would be a positive one. But then, if n is equal to 2, I will have the exponent of 3. So this will turn into negative 1. So I'll have minus 1/3. Is that right? For n equal hold on. For n equal 2, this will be 1/2, and this will be 3. For n equal 3, this will be positive, and 1/3. Okay, and then minus 1/4. So you can see that not all terms, right, or the values of the function are positive. So the conclusion is we cannot use the integral test. Alright. So a couple, maybe let's do a couple of problems, but alright. So problems or practice. Alright, let's start with something like this. So this is my series, so it goes like this: 1/1000 plus 1/1001 plus 1/1002, 3, and it keeps going, right? And the question is, does it converge or diverge? Okay, so I'll have 4 problems for you. And this one looks like this. I have space on the other side. I do. Okay, so n equals 5, infinity, and e to the negative n. Okay, number 3. Maybe I have 5 problems. So this one is infinity, n equal to 1, and I have 1. What is that? 1/n2π. Okay, so that's problem 3. Problem 4. Okay, is this one? trying to find some good problems. Okay, n equal to 1 that we haven't seen before. And square root of n squared plus 1. And the last one, number 5, is from n equal to 2 infinity and 1 over natural n times natural log of n. Okay. Alright, so look at those series and do some work, do some thinking, and figure out whether those series converge or diverge. Okay. Alright, so I hope you figured it out. You're back, and let's think about the first one. So the first one, right? You can look at the numbers, and they're getting closer to 0. So you may think, maybe this series converges. But if you look at it closely, right, and if you compare it to this one, right? So 1 over 2 plus 1 over 3 plus 1 over 4. Well, that was the harmonic series, right? And you see that this is the same series. This one is just a piece of this, of the regular harmonic series that's just farther away, right? So this, since this is a harmonic series and harmonic series diverges, so this diverges. Okay, how about this one? Okay, that n equal to 5 doesn't really matter, right? Because if series converge, it converges everywhere, right? And it doesn't matter which part of that series you take. So this, what is that? So this is a geometric series, so it's 1 over 2.71 to the power of n, right? So that series converges. R is between R is between between -1 and 1. So it converges, right? So it's 1 over 2.71. I had to think about it a little bit. Okay. Now number 3. So pi is 3.14, right? And this is a p series, so we can just, based on this, so p is greater than 1, so this one also converges by, we can write p series p greater than 1, so converges. Okay, so this one, if you write a couple terms, you can see that the terms are not getting closer to 0. So terms don't tend to 0. So the conclusion is diverges. And this one also diverges. Yeah, this one you need to do some work, right? You need to do that integral test. The diverges by integral test. Okay, so this one was harmonic series. And this one was geometric series. With R, absolute value of R less than 1. Alright, so that concludes the lecture on 10.4.